We are diving immediately into a critical piece of research for anyone serious about evaluating AI models. The paper is titled, How to Correctly Report LLM-as-a-Judge Evaluations by Chung-Paul Lee and colleagues.
And the central problem they're tackling is massive. We all use large language models now as a scalable evaluator, as the judge,
For everything, grading code quality, factual recall.
Exactly. But the issue is their raw judgment scores are inherently noisy and statistically biased.
And it's not a random bias, right? It's systematic.
Yeah.
The paper says if your model has genuinely low accuracy, the LLM judge tends to, inflate the score.
It inflates it. And if your model is already really good, high accuracy, the judge tends to drag the score down.
Which means it can completely mask true progress or exaggerate failures.
But the good news is the paper gives us a complete statistical fix. It's really built on 3 pillars. First, a simple estimator to correct that bias. Second, a proper confidence interval that accounts for all the uncertainty from your big test set and your small human verified set. And third, a really clever adaptive algorithm to make that human calibration super efficient.
So the bottom line, the payoff here, is you get a principled way to report your LLM results, you get reliable estimates, and you know exactly how certain you can be.
Yeah, you can finally trust that the gain you're seeing is a true model improvement and not just, noise from the evaluation itself.
Okay, let's really unpack that core problem. We've all done it right. We take the raw proportion of correct judgments, what the paper calls. It feels so intuitive. Why is it so misleading?
Because the LLM judge isn't perfect. It's that simple. Just like a human, it makes mistakes. And to understand those mistakes, we actually have to borrow some concepts from clinical diagnostics.
That's where specificity and sensitivity come in, right?
Exactly. Specificity, which they call T11, is the judge's true negative rate. So the probability it correctly says an incorrect answer is incorrect.
Yeah.
And then sensitivity, Q11L1, is the true positive rate. The probability it correctly marks a correct answer as correct.
And the moment either of those isn't 100%, bias just starts creeping in.
Oh, absolutely. I mean, think about the extreme case. Let's say your LLM judge is just overly positive. It loves saying correct.
Okay.
So it has perfect sensitivity, Q11 element, but terrible specificity, 2 all. That means it never, ever correctly identifies an incorrect answer. It just stamps correct on everything that comes across its desk.
Wow. So in that case, your raw score, your LLM would be 100% all the time. It wouldn't matter if your model was 10% accurate or 90% accurate. The score is completely meaningless.
Completely. And what's really fascinating is how that imperfection creates the systematic bias we talked about. The paper shows the naive estimate, hap hitter, creates this sort of S-curve when you plot it against the true accuracy. Taina Asochinaler.
Walk me through what that S-curve means for an engineer. What's the practical consequence?
Okay, so take a typical imperfect LLM judge. Let's say it has a specificity of 0.7 and a sensitivity of 0.9.
Pretty realistic.
Yeah. So when your model's true accuracy is low, say, the theta is 0.4 cents, the judge actually overestimates it. It might report a % Harvard Sathwelv. But when your model's true accuracy is high, the theta is $0.95, the judge underestimates it, maybe reporting ahead of only $0.90.
So if I'm comparing two models, one at 40% and a new one at 60%, the LLM judge might actually make that 20-point gap look smaller than it really is.
It shrinks the gap. And worse, if you're comparing two really good models, like one at 92% and another at 95%, that critical 3-point gain might get shrunk down to just 1 point. You might miss the improvement entirely.
So you could dismiss real progress just because of the tool you're using to measure it.
Precisely. We need a way to adjust for that, to get back to the ground truth.
Okay, so we need a mechanism to basically peel away that LLM's imperfection to see the real score, the thetas underneath. The paper uses a classical statistical tool for this.
It does. It's a result from prevalence estimation, the Rogin and Glayton formula. It's a way to correct an observed score, if you know the judge's clause, the Tauler-Lauren one.
But we don't know the true flaws, right? We have to estimate them.
And that's where the calibration dataset comes in. This is the part that requires that expensive human verification.
Right, so you have to get humans involved.
Yes, you have to commit to manually checking a small subset. You collect, say, $N$ examples that humans confirm are genuinely incorrect, and $M1 examples they confirm are correct. Then you run your LLM judge over just that little set to estimate its personal flaws to get your $N$.
Let's talk about the pain point there, though. Finding those samples can be really hard. If my model is already pretty good, finding enough truly incorrect answers, enough none-all ones, might be tough.
It's a real challenge. Or if your model is terrible, finding enough truly correct answers $1 is the hard part. But that difficulty is exactly why the method is so important. You're spending that effort to get high-quality human labels.
To make all the cheap LLM judgments trustworthy?
Exactly. Once you have your estimated flaws, $6 you can plug them into the bias-adjusted estimator.
And the idea there is basically it takes your raw score and just stretches or shrinks it based on the LLM's known imperfections.
It's a projection. It projects that biased score back onto the line of true accuracy. And the paper shows that even with estimated flaws, this new HETA has way less bias than the naive HET. It really works.
But just correcting the number isn't enough, right? For a publication, for a real deployment decision, an estimate is kind of meaningless without robust error bars. We need a confidence interval.
And this is where things get really interesting and where standard methods just completely fall apart.
Why?
Because in this LLM-as-a-Judge setup, you have not one, but two different sources of randomness you have to account for.
Okay, so wait. What are the two sources?
First, you have the test dataset uncertainty. That's from your main test set of size done. It's the randomness that affects your raw score.
Okay, that's the standard one we always think about.
Right. But then you also have the calibration dataset uncertainty. This is the randomness from your much smaller human-labeled sets, $100 and $N. That uncertainty affects your estimates of the judge's flaws, $100 and unders.
And if you ignore that second source of uncertainty,
You'll be wildly overconfident. Your confidence interval will be way too tight, and its actual coverage, the chance it contains the true value, will be terrible.
so you need some serious statistical machinery to combine all that variance. The paper uses the delta method, but how do they stop it from breaking when the sample sizes are small?
That's a great question. They use a crucial stabilization trick. It's a technique called add 2 successes and 2 failures. It's basically a form of statistical smoothing.
Why do you need to smooth it?
Well, imagine your judge gets a perfect score on your tiny calibration set. Maybe it gets 10 out of 10 correct for specificity. The standard math for variance can, explode or become unstable at those boundaries of 0% or 100% error. Adding those 2 virtual successes and 2 failures just pulls the estimate slightly away from the edge, making the whole calculation much more stable and reliable, especially for small calibration budgets.
And the results in the paper bear this out, the naive confidence interval.
Yeah.
It just failed completely, right?
Dramatically. It had nearly 0 coverage for many values. It was useless. But their proposed adjusted CI, which accounts for everything, it stayed reliably right around the 95% level it was supposed to.
That's the smoking gun, really. You have to do this to be statistically sound.
Without it, you're basically flying blind.
Okay, so that brings us to efficiency. We've accepted calibration as necessary. Now, how do we manage the resources? LLM judgments are cheap, so we can make our test set, huge.
As big as you want. And as the test goes to infinity, the uncertainty from the test set basically vanishes.
So the whole game becomes about the length of your confidence interval being determined by the expensive part, the human-verified calibration sets. $200 watt.
Exactly. So optimizing how you allocate those samples becomes the single most important thing you can do.
And the intuitive first step would be to just split the budget down the middle. $N equals $1. Is that what you should do?
It's the most common approach, but the paper proves it's often statistically suboptimal. You actually get the shortest, tightest confidence interval by allocating your samples asymmetrically.
Why asymmetrical? What drives that?
It's driven by 2 things. First, the judge's own specific flaws, and second, the distribution of your test results. You need to put more effort, more human labels on the side that's introducing the most noise into your final estimate.
So how on earth does an engineer figure out the perfect split before they've even done the calibration?
They don't have to. That's the beauty of their algorithm 1, the adaptive allocation algorithm. It's so smart. You start with a small, cheap pilot calibration sample.
Okay, a little test run.
Yep, just enough to get some preliminary estimates of your judge's flaws and $0.50 under, and your test set's raw score.
So that pilot study gives you a rough picture of the landscape.
Exactly. From that, you compute an error ratio, which basically measures how much worse the judge is at spotting incorrect answers versus correct ones. And then you look at your raw score.
Amen.
Then the optimal allocation rule uses those pilot numbers to tell you how to spend the rest of your budget. For example, if your model has very low accuracy, so HAL is small, the formula tells you to heavily weight your sampling towards the negative calibration set, $3.
So if your model is making a lot of mistakes and your judge is also bad at spotting mistakes, the algorithm adaptively says, hey, Stop wasting money verifying the few correct answers. We need way more data on the incorrect ones to nail down the judge's true error rate.
You got it. You allocate resources where the information gain is highest. The empirical results on this are crystal clear. For the same total budget, the adaptive strategy consistently produces much shorter confidence intervals than a simple 50-50 split.
It's literally getting more statistical certainty for your money. That's a huge deal.
So, to kind of wrap it all up, this framework is a toolkit that moves ML engineers and researchers out of the statistical dark ages of evaluation.
We're moving away from just trusting a raw score that we now know is noisy and biased.
And we're moving towards an unbiased estimate that comes with a proper, robust confidence interval that correctly combines variance from all the moving parts, num dollars and m dollars.
And crucially, it's not just theory. The authors provided a plug-in Python library to do all of this, right? The bias correction, the CI, the adaptive sampling.
Yes, it's designed to be used out of the box.
So I think the final major takeaway here, the biggest lesson for anyone allocating a budget, is that to reduce uncertainty in LLM-as-a-Judge evaluations, the answer isn't just to scale up your test set in dollar anymore.
No, that's not that bottleneck.
The key to reliable results is actually to optimize the design of your calibration dataset. How you choose your M$ and M$ is where the real statistical leverage is.
That's the entire game change. Reliability comes from smart experimental design, not just brute force compute.
You know, this work really exposes a fundamental vulnerability in how we've been doing things. Given how sensitive an LLM's reliability, those clears and clear-all flaws are, to the specific task, makes you wonder, what existing highly cited LLM benchmarks might need to be completely reevaluated with these corrections? How many state-of-the-art gains we've read about were actually just artifacts of a biased LLM judge? You might be sitting on a better model right now and you just don't know it because your judge was too pessimistic.